In July 2026, the Linux Foundation and Meta AI released PyTorch 3.0. This release departs from typical syntax updates, introducing a completely rewritten compilation layer. The update is engineered specifically to optimize how deep learning workloads map directly to enterprise hardware. This split-screen image illustrates the divide between high-level logic and hardware reality. On the left is standard Python code formatting, the basic import torch scripts used for development. On the right, the dense hardware memory addresses mapping natively to a GPU grid. For years, AI workloads relied on heavy, unoptimized interpreter abstractions to manage execution. PyTorch 3.0 bypasses the Python interpreter entirely through a new ahead-of-time compilation architecture. Understanding this transition from code abstraction to hardware-level execution defines the boundary between high-level script writing and the systems engineering required in 2026. To understand why the compiler was rewritten, we have to examine the historic execution standard for early iterations of PyTorch, eager mode. Eager mode allowed you to debug code line by line, functioning identically to standard Python scripts. However, that developer convenience carries a severe computational tax. This flowchart shows the mechanical bottleneck. Individual lines of text drop sequentially into the Python interpreter, dripping isolated data blocks into the GPU. The sequential orchestration forces tensors to pass one by one, creating a physical backlog and massive hardware latency. When you scale up to heavy multi-agent inference workloads, this sequential processing delay becomes a primary failure point for system performance. Eager mode prioritizes developer convenience over raw hardware speed, making it structurally unsustainable for the scale of modern deep learning. PyTorch 3.0 addresses this by abandoning sequential text execution. Instead of sequential text, PyTorch 3.0 captures model code as a mathematical dependency graph. The ahead-of-time inductor compiler analyzes this entire structure before execution. It fuses the node pathways into a single, unified block of native C++ kernels, routing directly to the GPU. The result is that the Python interpreter is completely bypassed. By mapping logic directly to custom silicon, we unlock blazing native hardware processing speeds that were previously unreachable. Shifting from literal scripts to unified mathematical graphs aligns software architecture directly with enterprise hardware processing. The most critical memory optimization mechanism built into this new compiler is called structural fusion. Legacy execution requires two distinct round trips to GPU VRAM for sequential operations, like matrix multiplication and activation. Structural fusion recognizes these steps, merging the separate mathematical actions into a single execution node. Now, the path requires only one read-write cycle from the VRAM. Removing that unnecessary memory round trip accelerates training performance natively by up to 40%. It also reduces token overhead during live inference workloads. Raw compute power is rarely the actual ceiling in deep learning. Memory bandwidth is the true bottleneck, and structural fusion provides the mechanical solution to reclaiming that bandwidth. This brings us to why this compiler rewrite became a technical necessity. This table compares execution profiles. On the left, a shallow classification task demands minimal memory and executes efficiently on a local CPU. On the right, massive deep learning transformers require vast, distributed tensor spaces mapped across parallel hardware architectures. Shallow architectures do not trigger the severe VRAM bottlenecks that make fusion layers necessary. But when managing the tensor spaces of a modern transformer, advanced parallel layout planning across distributed hardware is mandatory. Importing massive pre-trained architectures without understanding these physical memory differences leads directly to system failure in production. This transition redefines the technical skills required to build and deploy modern AI. The engineering mandate for 2026 is visible here. First, move past high-level API wrappers and simple import scripts. Study how different compilation layers operate beneath the framework surface. Analyze exactly how memory layouts dictate hardware execution speeds. Use PyTorch 3.0's graph compilation features to benchmark token latency directly within your validation pipelines. This is the profile of a hardware-aware software engineer. Success in the current AI landscape belongs to the system architects who understand how mathematical execution translates natively to metal hardware. If you want a hands-on tutorial for compiling a custom transformer graph using PyTorch 3.0's new backend engine, let me know in the comments. Class dismissed.